Hi students, welcome back. This is Plus One Computer Science and Computer Application, Chapter 2, Part 2 video. Before getting into the video, please do subscribe. In the previous class, you have learned about data representation and now we are going to learn about number systems. Here we do have four different types of number: decimal number, binary number, octal number, and hexadecimal number. So you'll be learning about all these number systems in detail. So let's see one by one. First of all, let's see what is numbering system. The most commonly used numbering system in real life is decimal number system. So from lower classes, you're learning only decimal number system. For addition, for subtraction, in mathematics, most of the numbers are from decimal number system. Even serial number, roll number, Aadhaar number, phone number, every numbers comes under this decimal number system. Day to day life, we are using decimal numbers. Other than decimal number, we do have binary number, octal number, and hexadecimal number. See, all these three numbers are mainly used for the electronic device, that is computer. And this decimal number is used for real life. And each number is uniquely identified by its base value or radix. So you will be learning what is base value or radix, and that is the count of number of digits in each number system. How many numbers are there in one number system? For example, decimal numbers, we do have 10 numbers, that is from 0 to 9. So the base value for decimal will be 10. So like that, each numbering system has its own base value or radix value. So let's start with the decimal number system. Decimal number system, these numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Total we do have 10 digits in decimal number system, and upcoming numbers are the combination of all these numbers. So the base value for decimal number is 10. You can say it as base or you can say it as radix. Both are same. So base value for decimal number is 10. So this means that each digit in decimal number system is multiplied by 10 raised to the power corresponding to digits position. That means ones, tens, hundreds. So based on the position, we have to multiply by 10 to the power terms. Decimal number system. So the base of decimal number system is 10, and here we do have an example 123. If you want to represent this as a decimal number, write the base 10 below the line level of the given number. So 123 base 10 is a decimal number. Now let's expand this decimal number to understand even better. So every single digit in decimal number is multiplied by 10 to the power terms. So let's see how it is done. First, let us take the least value, that is 3. 3 is in ones place, so we should multiply by 10 to the power 0. Number 3 is in ones place, so we should multiply by 10 to the power 0, which is equal to 1. And the next number is multiplied by 10 to the power 1. It is in tens place, so we have to multiply by 10 to the power 1. And then the next number, that is 1 into 10 to the power 2. So keep doing this multiplication process, and you have to increase the power term for every single digit. So let's calculate this. 1 into 10 to the power 2 is 100 plus 2 into 10 to the power 1, that is 2 into 10, 20, plus 3 into 10 to the power 0. 10 to the power 0, the value is 1. So 3 into 1 is 3. Now do the addition. So we do get the result as 123 base 10. So this way we represent decimal number system. So each digit in decimal number is multiplied by 10 to the power terms based on the position value. We start from the lowest digit, that is 3, ones place, then tens, then hundreds. It goes on in this pattern. So this is the way to represent decimal number system. So let's see other numbering system. So the next numbering system is binary number system. And yes, here we do have only two digits, that is 0 and 1. So this 0 and 1, they are actually called as bit, that is binary digit. Let's see an example. Here we do have 1101. So like decimal number, here in binary number also we do have positional value. So let's see, the rightmost bit is actually called as least significant bit. This least significant bit is having the lowest value, and the leftmost bit is called as most significant bit, which means it is having the higher value. So here the number in binary system are represented to the base 2, and the positional multipliers are the powers of 2. In the previous one, that is decimal number, we multiplied every single digit by 10 to the power terms. Here what we are going to do is each bit is going to be multiplied by 2 to the power terms, so that you will find the decimal equivalent of this binary number. Binary number system, base is 2. So for example, let us consider 1101 as the binary number. Base is 2, you should write below the line level. This is 4-bit binary number. And if you want to identify the decimal equivalent of this binary number, every single bit in this binary number should be multiplied by 2 to the power terms. So let's do it. First, the least significant bit is taken and we should multiply by 2 to the power 0. Do remember, always we will start with the power 0. And then the next bit, 0 into 2 to the power 1 plus third bit, that is 1 into 2 to the power 2. And the most significant bit, that is 1 into 2 to the power 3. So now you have to calculate this. 1 into 2 to the power 3, that is 2 into 2 into 2, the value is 8. 8 into 1 is 8 plus 1 into 2 to the power 2. 2 to the power 2 is 4 into 1 is 4 plus 0 into any number, the result is 0 plus 1 into 2 to the power 0. 2 to the power 0 value is 1. So 1 into 1 is 1. So do addition for all these numbers, that is 8 plus 4 plus 1. The result is 13. We have to write the base as 10 because this is decimal value for the given binary 1101. So this is the decimal equivalent for the given binary, and this is the way to identify the decimal equivalent for this given binary number. So this is binary to decimal conversion. So let's learn how to write nibble numbers, that is 4 bits. Here in this table I have written 0 to 15 decimal numbers, and I have left place to write binary 4 bit, and this is the positional value for binary. So first of all, nibble means it is collection of 4 bits binary number. So let's write binary number, and we do have an easy trick for writing this 4-bit number. It is simple. From 0 to 15 you can write the binary number using this simple trick. First let's consider the first column, that is 2 to the power 3. 2 to the power 3 is 8, so you should write 8 times 0 and 8 times 1. So simply fill the column with 0. 8 times you have to write 0 up to 7. And then you have to write 1. Up to 15 you have to write 1. So fill the column with 8 zeros and 8 ones. And then 2 to the power 2, that is 4. So 4 times you have to write 0 and then 4 times 1. Continue again, 4 times 0 and 4 times 1. The next column is 2 to the power 1. The value is 2. So 2 times 0 and 2 times 1. You have to fill the column like this, 0 0 1 1. So 2 times 0, 2 times 1. Write carefully, should not miss anything. Last one is 2 to the power 0. It is, the value is 1. So alternatively you will write 0 and 1. You should start from 0. So start writing from 0 and then 1. 0, 1. So take time and write. Be careful while writing. You have to write all these numbers in correct order. And 1. To check, you have to see the first row. All the bits in the first row should be 0. And the last row it should be 1. All 4 bits should be 1. And first column 8 times 0, 8 times 1. Second column 4 times 0, 4 times 1. Third column 2 times 0, 2 times 1. And the last column 0, 1, 0, 1. In this order if you write, then the table is correct. Here look at this binary number 1101. Simply you can check the value of this binary number, that is decimal value of this binary number, using this nibble table. So look at the number 1101, the decimal equivalent is 13. Instead of doing all this calculation, you can simply check the nibble table and write the answer. If the given binary is 4-bit, simply check the nibble table and equivalent decimal value you can write it. The next one is octal number system. In this octal number system, we do have 0, 1, 2, 3, 4, 5, 6 and 7. This many digits are there. That is total 8 digits are available in octal number system. From the decimal numbers, they have removed number 8 and 9. The 8 sequence and 9 sequence are completely ignored in this octal number system. So here each digit has its own positional value or weight as a power of 8. So similar concept, let's see with an example. Octal number system. The base of octal number is 8, which means 0 to 7 numbers are there. These many digits are there. Total 8 digits are there. So the base is 8. Now let's see the number sequence, how these numbers are written. So let's start from 0, 1, 2, 3, 4, 5, 6, 7. After 7, there is no 8, there is no 9. So what will be the next number? Yes, it is 10. Then it goes like this. All the 8 sequence and 9 sequence are removed from the decimal sequence and the remaining numbers are meant to be octal numbers. So after all this number, after 10, what comes? 11 and so on. Up to 17, it remains the same. After 17, the number is 20. Yes, 18 and 19 is removed. And same way 21, 22 and up to 27 it is same. What will be the number after 27? Yes, it is 30. 28 and 29 sequences removed. Likewise, all the numbers will be followed the same procedure. So what will be the number after 77? No 78, no 79, no 80 sequence, no 90 sequence. So the next number is 100. So 8 and 9 is not available in octal number system. So now let's start with an example, that is 547 is an example for octal number and you have to write the base as 8. Now if you want to know what is the decimal equivalent of this number, what we have to do? The same procedure, you have to multiply every digit with the power of 8 terms. So start from the least number, that is 7. 7 into 8 to the power 0. Let me cover this. Okay. The next number is 4. So plus 4 into 8 to the power 1. And then third number, that is third digit, 5 into 8 to the power 2. The same procedure you have to follow with the power of 8 terms. Now multiply and write all the numbers. So 8 8s are 64, that is 8 power, and 5 into 64 plus 4 into 8 is 32. So you write the number directly, 32, plus 7 into 8 to the power 0. 8 to the power 0, the value is 1. So 7 into 1 is 7. Now what is 5 into 64? 5 into 64 is 320 plus 32 plus 7. Now add all the numbers, you will get the result, and the final result of this number is 359 base 10. This is a decimal number. 359 decimal number is written as 547 in octal number system. So for example, if the number is given as 548 base 8, then this number is considered to be invalid octal number. The reason is there is no 8 and there is no 9 in octal number system. And the last numbering system is hexadecimal number system. So it uses digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 6 different alphabets, that is A, B, C, D, E and F. So total we do have 16 digits, including this alphabets we do have 16 digits. So here from 0 to 9 is decimal number system and A to F is added extra to the numbering sequence. And each hexadecimal digits has its own positional value or weight as a power of 16. So let's check with an example. So hexadecimal number system, we know that base is 16 because it has 16 numbers. So before getting into the example, let's see the sequence. So the numbers are 0, 1, 2, 3 and up to 9 it is same as decimal numbers. And after 9 we do have A, then B, C, D, E and F. So what comes after F? Yes, it is 10. So between 9 and 10 we do have 6 alphabets. The value, decimal value for A is 10. So we will see that later, and all the alphabets has its own decimal value. So after this we do have 10. Then comes 11, 12, 13 and up to 19 it is the same as decimal number. Then 1A, 1B, 1C, 1D, 1E and 1F. After this 20. So between 19 to 20 we do have the same 6 alphabets. So it works like this. After 21 up to 29 it is same as decimal number, then 2A, 2B and it goes on. So hexadecimal number sequence is followed in this pattern. For example, let us consider number 25 as the hexadecimal number. You should write the base as 16 below the line level. So this number is hexadecimal number. Now if you want to identify the decimal equivalent of this number, you should multiply every single digit of this number by power of 16. So let's see how to do. The least value is 5. 5 into 16 to the power 0 plus the next number 2. 2 into 16 to the power 1. So calculate this value. 16 to the power 1 is 16 and 16 into 2 is 32. So write the number 32 plus 16 to the power 0 is 1. So 1 into 5 is 5. So when you add this number you get 37. So 37 base 10. So this is the decimal number. For the hexadecimal, given hexadecimal 25, the decimal equivalent is 37. Now look at this chart. You will get a clear picture of numbering system. See, decimal number 0 to 15 it is written in the first column, and second column it is binary number, third column it is octal and fourth column is hexadecimal numbers. Now for example, look at the decimal number 11. The same number is represented as 1011 in binary, 013 that is 13 in octal and B in hexadecimal number. So decimal number we use in our real life, and binary, octal, hexa, these three numbering systems are mainly used in computer. And in the next class you will be learning number conversion. So for example, if a binary number is given, you should identify the equivalent decimal number and octal number, hexadecimal number. Like this, converting the number is called as number conversion. And today you have learnt about numbering system. In this we have learned 4 different types of numbers, that is decimal, binary, octal and hexadecimal. At the same time, you have learnt about how to convert a given binary number to decimal number, octal number to decimal number, and hexadecimal number to decimal number. In the next class, once again, you will be learning about number conversion in detail. That's all for today. Thank you.